So as we jump into our Module 11, we'll be taking a look at Chapter 8 in our textbook, covering the topic of principal stresses under given loading. So within this chapter, we're going to examine members that are going to be subjected to simultaneous compression, bending, and torsion. And we're going to take a look at the stresses resulting from these such combined loadings. We're also going to learn how to determine the principal stresses in structural members and machine elements under given loading conditions. So within this module, some objectives, what we're going to do is we're going to describe how stress components vary throughout a beam, identify key stress analysis locations in an I-shaped beam, design transmission shafts subject to transverse loads and torques, and then also describe the stresses throughout a member arising from these combined loadings. So as related to our textbook, again, this is Chapter 8, and for your reading guide, this will be sections 1 through 3. So we're going to break down this module into two different sections. You'll have Module 11.1 and Module 11.2. For Module 11.1, we're taking a look at the principal stresses under given loading. So objectives within this module, we're going to take a look at the principal stresses in a beam, take a look at the design of shaft transmissions, and then take a look at stresses under these combined loads. So within this module, we'll go through the theory from these above topics, talk about our governing equations, look at some practical applications, and then go through some problem solving. So now as we get into Chapter 8, I want to take a look back and look at the topics that we've covered at the beginning of this module in our textbook leading up to this chapter. So in Chapters 1 and 2, what we did was we learned how to determine our normal stress due to centric loads. So simplified case there. Then as we got into Chapter 3, we then analyzed the distributions of shearing stresses in a circular member due to a twisting couple. From there we went to our Chapter 4, where we looked at the normal stresses caused by bending couples. And then in Chapters 5 and 6, we went ahead and evaluated our shearing stresses due to transverse loads. Then we moved on to Module 7, or Chapter 7, and we learned how the components of stress are transformed by a rotation of coordinate axes and how to determine the principal planes and principal stresses and the maximum shearing stress at a point. Now as we jump into our Chapter 8, what we're going to do is learn how to determine the stress in a structural member or machine element due to a combination of loads. So now it's getting more realistic and more complex. And from there, how to find the corresponding principal stresses and our maximum shearing stress. So everything we've seen in Chapters 1 through 7, we're still going to come back into play here as we get into Chapter 8 and utilize a lot of that information, theory, and governing equations we saw before. So let's take a look now at the topic of principal stresses in a beam. So specifically here, let's take a look at a transversely loaded prismatic beam. So for this beam here, we can see we support it here over at point B. We have this other support here at D. We have a distributed load, W, acting between points D and B. Then we also have over here at the end at our point A, we have our point load right here, P. What we can also do is take a look here and draw a section right at C. So if we draw our section at C right here, we can see now, so neutral axis right there, there's our x direction going out here. If we go up to the element of interest right here, this is our direction y. So we're going up our y-axis, this distance of y right here, up to this element of interest that we're looking at here. So that's our distance there. Now what we can do for this particular example here is take a look at equations 8.1 and 8.2 in our textbook. So these are for a prismatic beam that's going to be subjected to transverse loading, as we saw in this diagram in our top left here. At 8.1, what we have here is our sigma x, our normal stress in our x direction. So there's our x direction right here. So we have that normal stress in our x direction. We can see that right there. So for this, what we can see, this is equal to a negative, our moment times y, where y is that distance going from our neutral axis up to that element right here where our sigma x is. And this is all going to be divided by our moment of inertia I. Now, what if we wanted our sigma m right here? So m, we can see, relates to this stress element up here at the very top surface. So at the top surface, our outer surface right here is at C, as we defined before. So that is our distance from our neutral axis all the way to the outer surface, in this case here, of our prismatic beam. So now, for sigma sub m, our normal stress there for that element, this is equal to our moment, this is positive now, times that distance C right there, divided by our moment of inertia I. So now taking a look at our sigma sub m, we can recall from previous chapters and modules that within our elastic limit, the stresses on a small element with the faces that are perpendicular to our x and our y axes reduce to a normal stress here of our sigma sub m if the element is at the free surface of our beam. Now, if we want to take a look at our shear stress rather than our normal stress, we can go to our equation 8.2. So in 8.2, we have our tau xy. We can look back over here at our diagram for stress elements at a selected point on our beam. There's our tau xy right there. We see that this element is our distance y off of our neutral axis here. And this is given by a relationship of negative V times Q over IT, where V is our shear, Q is the first moment about the neutral axis, I is our moment of inertia, and T is the width of the cross section at that point. So now we can also, from this here, take a look at our T sub m, where similarly to our sigma sub m up top, we can look at our T sub m in those relations as well. These are the shearing stresses related to this equation over here if the element is at the neutral axis. So we can come right here, there's our neutral axis right there. So our element's at the neutral axis. So now we have our T sub m is equal to V times Q over IT. And we can see now the difference is here, there's no negative sign. So our sign convention is now different. Now, if we think about our principal stresses, we realize that we can go back to our chapter 7, and these are determined by the methods that we saw in that previous chapter. Now, with that, we can ask ourselves the question, can this maximum normal stress within the cross-section be larger than our relationship here, our sigma sub m, given by this relationship we saw up here at the end of 8.1, which is equal to our m times c over I? Well, the answer to this question is going to be obtained by investigating the distribution of the principal stresses in a narrow rectangular cantilever beam that are subjected to a concentrated load that we'll call P at its free end. So if it can, then in order to determine this, the largest normal stress in the beam involves more than just this simple computation of our maximum moment. So as we continue on with the question of if we can have a maximum normal stress within the cross-section be larger than that relationship for our sigma sub m, we can take a look at our diagram on the top left here, where we're looking at the distribution of the principal stresses for this narrow rectangular cantilever beam supporting a single concentrated load, our P, right here. So we can see our stress element here. We have our sigma x, our tau xy, and this is a distance off our neutral axis of y. So we can recall that the normal and shearing stresses at a distance x, so here's our distance x from the end of where the load P is located, and at this distance y above our neutral axis are given with the relationships that we can see in our equations from our textbooks 612 and 613. I have these here, so our sigma x right here, sigma x is equal to that load xy all over our I. We can see down here our I is given by this relationship here. And this is also, if we reduce this down a little bit now when we plug in for our I, we can see this is P times xy over 1/3 AC squared. Rearrange, just put our 3 up top, and as we have now 3 times P over A times xy over our C squared. And C, we can see here, is our distance from the neutral axis to the outer surface right there. Now our tau xy, this relationship here, is equal to 3/2 P over A times 1 minus our y squared over c squared. That's our y right there, our distance up to our element, and our c again is that distance from our neutral axis to the outer surface. So as we're interested in answering that question about our sigma m and our sigma max, we can go back to our chapter 7 in our textbook, and we realize that we have relationships there and equations in order to determine our sigma max for any point on our beam. Now, the results for our sigma max and our sigma m are shown in this table up above here in the top right. So within this table here, we can see a ratio between our sigma max and our sigma m, as well as our sigma min and our sigma m as well, all laid out in this table. Now for this here, we do it based upon this diagram here for x is equal to 2c and x is equal to 8c. Now in each of these sections, the ratios have now been determined, as we can see along the side over here, this ratio of y over c for 11 different points. And the orientation and the principal axis has been indicated as well, so we can see from these diagrams here. So let's zoom in on this a little bit closer so we can get more detail out of this figure from our textbook. So we can see over here on the left, we have that diagram. There's our load P. Cantilever beam right there. It's our neutral axis where y is equal to 0. At the top surface, there's our y is equal to c. At the bottom surface, there's y is equal to negative c. And we're looking at these two areas of interest right here, when x is equal to 2 times our c value there, and x is equal to 8 times our c value right here. So again, this chart, what this shows is a distribution of the principal stresses in 2 transverse sections of the rectangular cantilever beam supporting a single concentrated load. So that P is our single concentrated load there. Now again, we're doing this at x is equal to 2c and x is equal to 8c. So we can take a look here at our ratio between our y and our c. And again, we recall our y is the distance from our neutral axis to our point of interest right there. And c is equal to the top and bottom surface, and our y is at the top surface, or the bottom surface is our y and negative y. So our ratio between our y and c, when this is 1, so those are equal to each other when y is equal to c, we have our sigma min over sigma m is equal to 0, and our sigma max over sigma m is equal to 1 there. And here's our orientation. So now we can go down through for these different values for our y over c and see our ratios between our sigma min and sigma m and our sigma max and sigma m. And this is again for x is equal to 2c. Now we can also take a look over here when x is equal to 8c at this location out here, and we can see again for when our ratio is equal to y over c is equal to 1, then we have our sigma min over sig m of 0 and our sig max over sig m of 1 there, and these continue on and so forth all the way up here until we get to a y over c of a negative 1. So we go all the way up from 1 up to 0 and then to a negative 1 for both x equals 2c and x is equal to 8c. So after taking a look at this table, it becomes clear that our sigma max is going to be smaller than our sigma sub m in both of these two sections where x is equal to 2c and x is equal to 8c. Now, if it is going to exceed our sigma sub m elsewhere, it could be close to our load P right here. So if we are going to see this exceeded, it's going to be right at the end here, close to this external load P at the end of this beam. And this is where our sigma sub m is going to be small compared to our tau sub m. But a thing we want to note here is that as we get closer to this end where our load P right here, our Saint-Venant's principle no longer applies as we get close to the end of this load right here, where our P is at the end of the beam right there. And therefore, our equations 8.3 and 8.4 from our textbook, so these equations here, cease to be valid. So now as we continue on with our topic of the principal stresses in a beam, when we looked at our rectangular beams, the maximum normal stress in the beam we found could be obtained by the following relationship from 8.1 in our textbook, that sigma sub x is equal to our negative m times y over I, where we saw we had a relationship based on geometry for our I. So this remains valid for many beams of non-rectangular cross sections as well. When the width of the cross section varies so that the large shearing stresses, our tau sub x, occurs at points near the surface. This is important here, it's near the surface, then our principal stress, our sigma max, may be larger than our sigma sub m. So this is the case where we can answer that question there, where we do have a sigma max that could be larger than our sigma sub m. Now, this is a distinct possibility when selecting our W beams, S beams, I beams, where we should calculate the principal stress, our sigma max, at the junctions B and D right here. So this is right here, there's our point B right there, there's our point D right there of the web within the flanges of our beam. This is a great figure to reference back to when we're looking at the key stress analysis for locations in our I beams. So now let's take this opportunity to apply some of that theory and governing equations we just discussed to an example problem. So here we'll take a look at example problem 8.1. Within this problem here, we have this initial diagram and our problem statement. Within our problem statement, they tell us that we have a 160 kilonewton force is applied at the end of, and they tell us the type of rolled steel beam we have right here, W200 by 52. So we can go over here to our diagram, we see, okay, there's our 160 kilonewton force applied to the end of this I-beam right there. And we can see we have this distance here given in our diagram from that load up to our section at A here, and this is equal to 375 millimeters. So a couple things we want to note with this. One, it's given to us in millimeters. Make sure we do the conversion if we want to go to meters. And two, it's being measured from the end of the beam here and not from the fixed point over here. Then I also see now, have our other view over here showing the shape of our beam. Now they tell us to neglect the effects of the fillets and of the stress concentrations, and ask us to determine whether the normal stresses satisfy a design specification that they be equal or less than 150 MPa at our section A and A prime right there where we have our dotted line. So again, if we were to solve this problem out by hand, our first step now would be to draw and create our setup page. We have all of our given information that's from our problem statement and our initial given diagram, all clearly labeled. And again, we have our four things that we're going to have there. We're going to have the variable name, we're going to have our numeric value, we're going to have our units, and then we're also going to have how it relates back to our problem. So those are the four things we want to include for your homework problems, exam problems on your setup page. So once we create our setup page, if we're solving it out by hand, we then come over here and decide, okay, what assumptions we can make. So we read through our problem statement. They tell us a couple things. If we're neglecting the effects of fillets and stress concentration, those are two assumptions that we're going to make, is that we can neglect those, and it tells us that right in our problem statement. So those are two things that we can include in our assumptions. The next thing we want to do, once we have that setup page created, is look at everything that we're given and everything they ask us to solve for right here in our determine section, which will be labeled as our find section on our setup page. And from there, we can come up with a procedure for analysis and any governing equations that we might be utilizing. So over here, we have our procedure for our analysis listed under solution. So our first step is going to be to determine the shear and bending moment in the section A prime. So there's this section right there. 2, we're going to calculate the normal stress at the top surface of the flange web junction. From there, we're going to evaluate the shear stress at the flange web junction. And last, we're going to calculate our principal stresses at that same flange web junction. So now as we begin our solution, we go back to our procedure for analysis, and we see that our first step here was to determine the shear and bending moment of our section at A prime. So what we do here is we draw this out. There's our section right there, A prime. Here's the end of our beam with that 160 kilonewton load on it, and this is our distance right now, and you can see we've converted this to meters instead of millimeters now. So we're at 0.375 meters from the end, the free end of our beam, to our section here at A prime. And at A prime, we now have our shear load VA, and we have our bending moment M sub A here. So this is our free body diagram of the beam with our section here at that A prime. So from our free body diagram, we can do out our equilibrium equation. So we can say, let's take a look at our moments first. The summation of moments are equal to 0 in equilibrium. So let's take the summation of moments about A. So we're going to have our moment here at A as being one of our moments. The other moment that's going to be about A is going to be our force here, 160 kilonewtons, times our perpendicular distance of 0.375. So from that there, we can solve that for our M sub A, and we can see that M sub A is equal to 160 kilonewtons times 0.375. We can solve this now for MA, say 160 kilonewtons times 0.375 meters is 60 kilonewton meters. And this is why it was important. We take a look at our units here. This is in newtons or kilonewtons right here, and this was in millimeters. We need to convert to meters to be in the same units here as our force there in order to get this answer here, which we end up with as kilonewton meters. Now we can do the same thing from our free body diagram and say, okay, let's do the summation of our forces. So the summation of forces is equal to 0 for equilibrium relationship here. So we can see our only forces acting here is if we have a positive and negative, let's just call this our positive x to the right, and we have our positive y going up, then summation of forces in our y direction is going to be a negative 160 plus our VA is equal to 0. So therefore, we can solve for that, and our VA is equal to 160 kilonewtons. So now that we've completed step 1 in our procedure for analysis and found our shear and bending moment, our M sub A and our V sub A, we have numerical values for these now in the correct units. Now what we can do is move on to step 2 in our procedure for analysis, where we're looking to calculate the normal stress at the top surface of the flange web junction. So right here at this point A is what we're looking for. So we have these two governing equations that we see here, where our sigma sub A right here at the top surface is equal to our M sub A, which we've already found right here to be 60 kilonewton meters right here, all divided by our S. So now, in order to plug into these two equations, let's go to our appendices in the back of the book for this type of beam that we're dealing with. So for this information for the beam that they gave us, they told us this was a W200 by, in this case here, 52 beam. So we go back to our Appendix E in the back of our textbook and take a look at the properties of our rolled steel shapes. Thing to note here, this is a W shape, a wide flange, and it is an SI unit. So those are things we want to pay attention to. We're looking at our units and our values they give us in the problem statement. They give us this generic diagram here with all of this information and the geometry here that's referenced from our Appendix E in the table here. So we look down, we say, okay, we're dealing with a W200 by 52. I've boxed this all in red. We can go back to our governing equations, and these equations come from our chapter 5 and derived from our 5.18 in our textbook. We have our sigma sub A is equal to our moment at A divided by S, which is our section modulus here, and we can look this up right from the table, but this is also from the relationship we saw back in that chapter of our I over C there. So for this here, we can go up. You see I've highlighted this in a blue square, so I go up here for our 52, look at our axis XX right here, and this is our 511 times 10 to the third millimeters cubed. So pay attention to your units for this here. And we can see we convert this later to meters. Now it's times 10 to the -6. So again, really make sure we pay attention to our units and everything that's given to us in these tables and make sure everything lines up correct when we do our unit analysis out. So we now have our denominator S here that we've pulled from our table here from Appendix E, and we can take a look at this and see what other information do we have. So let's complete our generic diagram and over here on the right and fill in everything that we have here. Let's take a look at our top left here. We have our T sub F right here. Now our T sub F, we come down to here. This is our thickness in millimeters, that top flange right there. So this is our 12.6. So we can pop up here and now we can see our T sub F we replace with a 12.6 right here for this thickness. Then we can go down here to our value for our D right here. So we can see our D is our depth in millimeters here, and this is 206 millimeters. So we fill that value in there. Now you can see they also give us our web thickness here, 7.87. So this is our T sub W right here, our web thickness, and that is a 7.87 that we can plug in over here as well. We can also get our I value. We come down here for our I. Pay attention to your units here. This is our 52.9. Converted to meters is 52.9 times 10 to the -6 meters to the fourth. So now if we have this value for our depth, our D right here of 206, we realize D goes the whole length right here, so this is 206 millimeters. If we want to find our C value here, this goes from our central neutral axis at C here all the way up to our point A there, so we can see that that distance there is going to be half of our 206, which is going to be 103 millimeters. So this is our 103 right there for our value for our C. And now we can go over here and say, well, what about our y sub b? Well, our y sub b we see goes from our neutral axis right here, point C, all the way to now our point B right there. So this is going to be minus the thickness right here, our 12.6, the thickness, our T sub F. So 103 minus 12.6 will give us a 90.4, again, still in our units of millimeters here, that we can plug in now for our value for our y sub b. So this brings us down to this equation here with a relationship for our sigma b and our sigma a, where sigma b is our stress right here at point B, and sigma A is at that outer surface right there, our sigma A. Sigma A we found a value for from this relationship from our 5.18 equation in our textbook of 117.4 megapascals. So we can plug in our value right here for our sigma A. There's our 117.4 megapascals. Now we can see we have over here our y sub b, which comes right from here, our 90.4 millimeters, divided by our C value that we just solved for right here, which is half of our 206, or 103 millimeters right there. We can plug into this here. Again, pay attention to units. In this case here, the millimeters cancel with millimeters, so we don't necessarily have to worry about converting to meters because units cancel out. Leave us just with megapascals. So our sigma sub b from this here is 103 megapascals. So now we can move on to step 3 in our procedure for analysis. In step 3, we want to find our shear stress at the flange web junction. So right here is our flange web junction down here at B. So we want to find our shear stress, our tau sub b. So our governing equation for our shear stress is equal to VA, our shear force, right there that we found at the very beginning of the problem right there from our equilibrium equation from our free body diagram, where we had 160 kilonewtons for our V. And this is times Q all over our IT. Well, our Q value is based on this relationship that we've seen here before, so we can plug in our known values for our Q relationship. So this is 206, our D value, our thickness right here, our 12.6 millimeters, and our Y value right here of 96.7. Now pay attention to this right here. Before we measured from our C to B and from C to A, notice this right here is going to the middle of this section right here, which would be 103 minus half of our 12.6 right there, which would then give us this value of 96.7 millimeters. Pay attention, this is in millimeters. When we do out our math, this is 251 times 10 to the third millimeters cubed. Convert that to meters, we end up with 251 times 10 to the -6 meters cubed. That now gives us a value for our Q that we can plug back in to find that shear stress at the flange web junction. So we plug that in there. This is all over our I that we pulled off of our appendix in the back of the book. 52 times 10 to the negative 6 meters to the fourth. Pay attention, everything needs to be in meters now. And this is time our thickness right here, which again, this was given to us from that table as well in millimeters of 7.87. So we convert this to meters here. What we end up with now for part 3, looking for that shear stress, our tau sub B is equal to our 95.6 megapascals. So now that we've completed our part 3 here, and we now have a shear stress at that web flange junction right there, we can now go to our part 4 of our procedure for analysis. And where this comes in is it relates back to in our problem statement when they asked us to determine whether the normal stresses satisfy a design specification that they may be equal or less to 150 megapascals at that section of interest. So we need to ask ourselves, does this design meet these specifications? Does it satisfy this? So in order to do this, what we're going to do is calculate the principal stresses at our flange web junction. So we can do this with Moore's circle and some of our governing equations. We now have multiple ways that we can solve things. So from our equation here, we can see that our sigma max is going to be equal to 1/2 of our sigma b, which we already have a value for. This is our 103, plus the square root of the sum of the squares of our 1/2 sigma b squared, plus our tau sub b squared. And we found this shear stress at our flange web junction up above here. So we have a value for this that we can plug in of 96.5. We have a value now for our sigma sub b that we can plug in as 103. We plug all of this in here, and we find out now that our sigma max is equal to 160.9 megapascals. This is greater than our 150 megapascals. So therefore, the answer to our question, the problem statement, does this satisfy the design specifications? No, the design specification is not satisfied because it's not less than or equal to 150. It is greater than 150 megapascals. So the next topic I want to take a look at within this module is the design of our transmission shafts. So one thing to consider when we're looking at transmission shafts is if the power is transferred to and from the shaft by gears or sprocket wheels, then the shaft is going to be subjected to transverse loading as well as torsional loading. So we can come over to the left here to our diagram where we see loading on a gear shaft system. So in the top part, in part A, what we have here is the forces applied to the gear teeth. So you have your P1, your P2, and your P3 applied right to those gear teeth there. Whereas down in part B, we now have our free body diagram. That's going to be useful for us as we're starting to get into some of our equations of our equilibrium equations and equations related to the rest of the problem. So this free body diagram of the shaft, we see here the gear forces are going to be replaced by equivalent force couple systems that are applied to the shaft. So you can see we have this torque right here. We have our P1 on the shaft, our torque 2, P2, torque 3, P3, and now you can see our support right here. We have our By and our Bz right here, and we have our Az and our Ay over there at the end of the shafts where it's supported right there and right there. Another thing we want to think about is the fact that our normal stresses due to transfer loads may be rather large, and that these should be included in the determination of our maximum shearing stress. But our shearing stresses due to transverse loads, these are usually going to be rather small, and the contribution to our maximum shearing stress may be negligible for this here. So this is something in your assumptions and your problem statement as you're reading through the problem statement that you want to take a look at. So as we continue on with the design of transmission shafts, we want to take a look at now is an example we see in the top left corner. We have torque and bending couples acting on a shaft cross section in part A right here, and in part B what we can see here is we have the bending couples are going to be replaced by the resultant. So we can see this M right here is the resultant of our MZ and our My. So this comes back to our relationships over here. We recall our normal force here. We have our sigma sub m is equal to our moment times that distance c out to the outer surface all over our moment of inertia, where now we have this m right there squared is going to be the sum of the squares of our my squared and our mz squared. So m is the square root of the sum of those squares. So again, here's our my. So we square this, add it to our mz squared there, and then this is equal to our m squared right over here. Now if we want to find our tau sub m for our shear stress, this is going to be equal to our torque times that same distance c to the outer surface, all divided by our polar moment of inertia, j. So now if we want to find the maximum shearing stress, or tau max, there's a couple different ways that we can do that. We have our basic equation that we can see here that our tau max is equal to the square root of our sigma m, which we have this relationship up here for our sigma m, divided by 2 squared, plus now our tau m, which we have a relationship for right here, squared. Take the square root of the sum of both of those and we can get our tau max. So we now have relationships for both of those. So if we plug in for our sigma m right here where we have our m, c over I divided by 2, we now have this relationship here. We have mc over 2I squared. Plus now if we plugged in for our tau sub m right here, for our shear stress, this is equal to Tc over J. So we can plug that in here. Now we can see we have Tc over J squared. Now, we can also take a look and draw more circle, which we have down here for more circle for a shaft loading. And we can see that our tau max, if we look at this here, is the distance from our neutral axis up to the outside edge, right here at point D. And this is the radius of our circle. So this is equal to our radius r. Now if we have a circle with an annular cross section, then we can see that our 2I is going to be equal to J. So we can replace this here with a J from this relationship there. And what we end up with for that is now that our tau max is equal to, we can pull this out front here, our C over J times the square root of m squared plus our t squared. So our moment squared plus our torque squared. We have the square root of the sum of the squares of our moment and our torque times our C over J. So with that, there is our shaft section requirement where we have that polar moment inertia J over that distance C minimum is equal to, we can see here we have the square root of the sum of the squares of our m squared plus our t squared max all over our shear stress allowable. So now let's apply some of that theory and those governing equations to an example problem. So we'll take a look here at sample problem 8.3 from our textbook. Within this problem, they give us our initial diagram. And within this diagram here, a lot of our dimensions are given. Everything is clearly labeled. We have all of our distances and dimensions up here. And they also tell us that our dimensions are given to us in millimeters. So that's something we need to pay attention to and make sure that we convert to meters as necessary. So now within our problem statement down here, it tells us that our shaft, our solid shaft AB, so this is our solid shaft from A to B up here in our diagram, this is going to rotate at 480 RPM. And it's going to transmit 30 kilowatts from the motor to our gears G and H. So this is our gears G and H right here. So 20 kilowatts, it tells us, is taken off at gear G right here. And 10 kilowatts are taken off at gear H over here. Knowing that our allowable shear stress is given to us as 50 megapascals, they ask us to determine the smallest permissible diameter of the shaft. So our goal here is to figure out what the diameter of this shaft AB is. So now if we were doing this problem out by hand again, we first create our setup page, read through this problem statement, realize, okay, they give us that this rotates at 480 RPM. We have our power over here of 30 kilowatts. We have our information here for how much is taken off at both of those gears. We have our allowable shear stress right here, and this is what they're asking us to solve for. So we use all that information along with all of the dimensions given up here in our initial diagram to create our setup page. So we'd have our list of all of our givens where we'd write out everything that we have here again with those 4 different components. We would have our variable that we're using, whatever that symbol is, whatever variable letters we're using and indices we're using. Then we would have our numerical value. Then after our numerical value, we would have the units that we're using. And then fourth, we would have how it relates back to our physical problem. So we do that for everything that's given and for everything that that's to solve for. Now, once we've had that, we make all of our assumptions on our setup page, and then we can begin our solution. And for our solution, we come up with our procedure for analysis. So for our procedure for analysis, what we have here is part 1. We're going to determine the gear torques and the corresponding tangential forces. From there, we're going to move on to find our reactions at A and B. So again, at A and B, we want to find our reactions at both of those points there. And then we want to identify the critical shaft section from the torque and bending moment diagrams. And last, we'll calculate that minimum allowable shaft diameter that asks us to solve for in our problem statement. So now let's break down that given information from our diagram and our problem statement, come up with our list of givens over here. So if our frequency, when we change it from RPM to Hertz, it's 8 Hertz. When we have our P here of 30 kilowatts when we're acting at E, then we can see down here 20 kilowatts at G and 10 kilowatts at H. So with that information there, what we can do is go to our governing equation here to find our torque at E. So at point E right here, take a look, and this is going to be our P, which at E right here is 30 kilowatts, all divided by 2 pi times our frequency, and our frequency we found to be 8 Hertz from our problem statement. So this is our 480 RPM, we convert that to Hertz, that's 8 Hertz right there. So we find now is that our torque at E is equal to 597 Newton meters. Now if we want to get our force, we can go backwards from our equation for torque right here, force times perpendicular distance, and take our torque right here divided by the perpendicular distance, which in this case here is our radius at E, right there. So that's coming out from right there. So if we take our torque that we've just found here, our 597, divide by our radius, converting it to meters rather than millimeters, of 0.16 meters, we find out that our force at E is 3.73 kilonewtons. Now we can do the same thing for C and D. So we come over here at C and we can plug in our value here for P is 20 kilowatts divided by 2 pi times 8 hertz. So this is 398 Newton meters. And our force at C was given to us is 6.63 kilonewtons in the problem. And at D we do the same thing. This is going to be our P right here is 10 kilowatts divided by 2 pi times our frequency of 8 hertz is 199 Newton meters times our F sub D, which is given to us as 2.49 kilonewtons. So with that there, we've completed our first part for our procedure for analysis, and we've determined the gear torques and the corresponding tangential forces for the first part of the problem. From there, the next thing that we want to do is take a look and find our reactions at A and B. So what we've done here is we've created our free body diagram for the shaft A, B, and its gears, and now we can see there's that F sub C, there's our F sub C there that was given to us, there's our F sub D with our F sub D, and now we have a value for F sub E, so we can plug this in down here with our F sub E. We do want to pay attention to our sign convention, make sure things are acting in the opposite directions. We give the appropriate sign convention with that. So we can see that we have, when we're looking at our reaction forces, what we're going to end up looking for next here, A and B, you can see you have something going up at both of those in the Y direction there, and you also have something coming out of the board at us here, and what would either be our positive or negative Z direction. So how we do our right-hand rule, how we define what's positive and negative becomes important quickly as we're doing our sign convention and move into this section here. We're looking for our reactions at A and B. Now what we can also do is we can create our free body diagram for shaft AB with our gear forces replaced by our equivalent force and couple systems. So there's our equivalent forces and couple systems up above at C, D, and E right there. So we have all of those. So at E you can see we have this 3.73 kilonewtons as our force. There's our 3.73 kilonewtons as our force there at E. And we have our torque of 597 Newton meters, our torque of 597 Newton meters. We can do this at D as well. For at D now we have our force here of 2.49 kilonewtons. So there's that there. And we have our torque here of 199 Newton meters right there. So now we can move up to C, where C, we have that torque specified here as 398 Newton meters, and we also have our force at C acting at 6.63 kilonewtons. So now this is our free body diagram. We replace those gear forces with our equivalent force and couple system. So now if we continue on looking to find our reactions at A and B, the first thing I try to do is to do out my equilibrium equations. So I'm decided to look at my forces first and see how far this gets us. So I have my diagram up here. This is my free body diagram of the shaft AB and its gears right there. So I say let's take a look at the Y direction first. Find my Y is positive going up, my X is positive going to the right. So what forces are acting in my Y direction? I come over here, well, I have my A sub Y, I have my B sub Y, and I also have this negative FE. So I say AY minus FE plus BY is equal to 0. So I can rearrange this a little bit. I know my value for my FE, so I can plug that in there. I say AY minus 3.73 kilonewtons plus BY is equal to 0. So I can move this over to the other side and say that AY plus BY is equal to 3.73 kilonewtons. So now let's take a look in my Z direction coming out here. If I use my right-hand rule, so my Z direction, I have a positive AZ, I have a negative FC, I have a negative FD, and I have a positive BZ right there. So I put those in and I say, okay, well, I have values for FC and for my FD. So summation of forces in my Z direction is positive AZ minus 6.63 kilonewtons minus 2.49 kilonewtons plus BZ is equal to 0. Now I look at these and I can come up with two equations that I've boxed in red. So I have two equations but four unknowns. So I'm going to need to find some more relationships because my number of unknowns are greater than my number of equations. So my next step I'm going to do is look at my moments. So as we continue to take a look at our moments, we draw out our free body diagram. I want to do this in my XY plane. I come down here and I say, okay, let's take my moments about A. Well, if I'm taking my moments about A, my A sub Y is not going to contribute, but my FE and my BY are both going to contribute. So I can say, okay, moments about A, this is going to be my FE, which is negative 3.73 times my distance of 0.6 meters, plus BY times my 0.8 meters. This one's going counterclockwise, this is going clockwise, therefore the sign convention equal to 0. Rearrange this and I say that 3.73 times 0.6 meters is equal to BY times 0.8 meters, where my BY is then 2.8. Now I can do the same thing, and I want to sum my moments about B. So when I sum my moments about B, my BY does not contribute, but my FE and my AY contributes over here. So I can say, okay, this is going to be my FE times 0.2, or negative 3.73 times 0.2 meters, and I have my AY times my 0.8 meters right there. Set these equal to each other, and now I can solve for my AY. My AY ends up being 0.932. So if we take a look at our moments as we look in our XZ plane now, we can take a look down here and we have our free body diagram drawn out. There's our shaft from A to B. We can see at point A, we have our reactionary force A sub Z, and at B, we have our reactionary force B sub Z. And we also have our F sub C and our F sub D. So all of these we're going to use when we're taking a look at our summation of moments. So first let's take our summation of moments about our point A. Summation of moments, point A, what moments act there? Well, our A sub Z is not going to contribute, but our F sub C, F sub D, and our B sub Z are all going to contribute there. So we can say for F sub C, we go up here, F sub C is 6.63 times a distance of 0.2 meters. Plus we have a 2.49, which is our F sub D here, times our distance of 0.4 meters. Minus now we have our B sub D times that distance of 0.8 meters. This is our equilibrium equation. This is equal to 0. One equation, one unknown. We can solve for our B sub Z, and our B sub Z is equal to 2.9 kilonewtons. Now let's take our moments about point B over here. So for point B, our B sub Z is not going to be contributing, but our A sub Z, F sub Z, and our F sub D all will. So we can say now here we have our F sub D, which is a 2.49 times our distance of 0.4 meters, minus our 6.63 from our F sub C times a distance of 0.6 meters, plus our A sub Z over here times a distance of 0.8 meters is equal to 0 for our equilibrium equation. One equation, one unknown. Our only unknown is our A sub Z. So now we can solve this and have a value for A sub Z. So from summing our moments, looking at our Y or our XZ plane, we could find our B sub Z and our A sub Z. So we can go back to take a look at our equilibrium equations from our summation of forces in the Y and our Z direction. And when we look at those, we do have a check here that we can plug in these values we found from the summation of our moments from those equilibrium equations. We can plug in our AY up here and double check that we get the same B sub Y. We can plug in our AZ here and double check that we got the same B sub Z. Or again, as I mentioned earlier, we could have just not done the moments in both of those planes, just did the moments in one plane, plugged back in, and solved for the other ones using our summation of forces. So just different ways that we could have solved this, but also great ways to utilize as double checks. So the next thing we want to do is draw out our torque and bending moment diagrams. So what we can do is we can start with the information we gathered earlier from our free body diagrams we used for our equilibrium equations and use those to draw out our bending and moment diagrams here in our torque diagram. So we can see if we start here with a free body diagram, we can see acting in our Y direction, we have these forces right here that we saw before, our reactions at A and B and our F sub E right there. We can utilize those by their distances in order to come up with our moment diagram that we see down here. So for our moment diagram, we have these values when we do this out. And what we see here from our moment diagram is that we have this value here for our M sub Y is 1160. So if we had 186 was 373 plus our 560, we get 1160 there. So now to find our max, it's the square root of the sum of the squares. So we do it now over here for our Z direction here. So we take a look at everything acting in our Z direction. We have all these forces here and their distances. We can come down here to this diagram. We end up with a 373 for our M sub Z. And for our torque over here, we found this earlier, our torque here was 595. So we can take the square root of the sum of those squares and we end up with a value here now for the max is 1,357 Newton meters. And this, again, is the analysis of the free body diagram for the shaft AB alone with equivalent force couple loads. And this is equivalent to the superposition of the bending moments from our vertical loads, horizontal loads, and our applied torque. So there's our vertical loads, horizontal loads, and our applied torques. So now if we go back to our problem statement or look back at our setup page for this problem, we realize we still have one more thing we need to solve for. What we want to do is calculate that minimum allowable shaft diameter. So for this, our governing equation is equation 8.7 in our textbook that we discussed earlier in this module, that our J over C, our polar order of inertia over that distance C, is equal to the square root of the sum of the squares of our My, Mz, and T that we just talked about and solved for on the previous page, all over our tau allowable right there. So that was given to us in the problem statement as 50 megapascals. We found the numerator of this, the 1357 Newton meters from our previous slide. And this value here for this ratio is 27.14 times 10 to the negative 6 meters cubed. Now, for a circular shaft that we have in this problem right here, we can use this relationship for our J over C, plug in for our J for our circular shaft, and we end up with is our pi over 2 times C squared. Right here is now equal to the right-hand side of this over here, which is that 27.14 times 10 to the negative 6. So in this case here, one equation, one unknown. Our only unknown is this C value right here. So we solve for this, and it's 0.02585 meters. So from this here, what we can do is plug back in and say that, okay, well, our diameter is equal to 2C, right there. So we can solve this now for our diameter. Then this becomes now, if we multiply our C by 2, that gives us that diameter there, because we call our C goes from our central neutral axis out to the edge of this, the outer surface. So our diameter would be 2 times that there. So that would give us a diameter of 51.7 if we convert back to millimeters. So now let's move on to the topic of our combined loads. So in the first couple chapters, we looked at stresses caused by centric axial load. Then we moved on and analyzed the distribution of stresses in cylindrical members subject to twisting couple. Then in chapter 4, we determined the stresses caused by bending couples. And then in 5 and 6, we went on to stresses produced by transverse loads. Well, now in this section here, we're going to determine the principal stresses in slender structural members or machine components undergoing fairly general loading conditions. What we mean by fairly general loading conditions is that there is going to be more than a single type of loading. It's going to be a combination of all these other types of loading that we saw above in our previous chapters. So as we continue on looking at their stresses under combined loads, let's take a look over here at this example where we have this member ABDE, which is subjected to several forces. So with this here, we can see there's our end A, we have our end here, and at each of the corners there's our B and our D. Along the way we have these forces F1, F2, F3, F4, and our F6 right here. And we can see at H and K we have our stress elements at a section that we're taking. So with this, we're going to want to determine the stresses in our structural member that are subjected to these arbitrary loads. So with these arbitrary loadings right here, what we want to do is we want to pass a section through points of interest. So if this is our points of interest right here, we'll cut a section right here. We're going through that where we labeled H and K for our elements right there. And at this point, we're going to determine our force couple system and at the centroid section required to maintain equilibrium. Well, what this means is we're going to cut this right here where our HK is. So we come down here and now we have a free body diagram for that segment ABC. So now we're just going up to where we cut that section right here at C, and then we can determine our internal forces and moments. So we talk about this required to maintain equilibrium. So it's saying from this free body diagram, we're going to do out our equilibrium equations. So we look at a free body diagram, what forces are acting in our X direction, our Y direction, our Z direction, what moments are we going to have. So with this, what we're going to do is we're going to come up with a system of internal forces that consist of our 3 force components and of 3 couple vectors. Let's take a look where our 3 force components. We have our F1, our F2, and our F3 right there, and we have our couple moments over here. We have our couple moment there, a couple moment there, and our couple moment here. So we have all of those there. The next step we're going to do is determine the stress distribution. How do we do this? We do this by applying our superposition principle. So now as we continue on looking at our stresses under combined loads, we want to take a look at this diagram in our top left. In this diagram here, we can see we have internal forces and couple vectors. Now we've separated these into 2 different parts of the diagram, parts A and part B. In part A, we have those that are causing our normal stresses. So we go over here to part A, we can see, okay, we have our My, our Mz, and our load P. Now in part B of this diagram here, we have those that are causing our shearing stresses. So we separated those out. For our shearing stresses, we have our shear loads right here, our Vy, our Vz, and our torque T there. So going back to part A, we can see we have this P here. What P is, this is our centric axial force that produces normal stresses in the section. We also have our couple vectors right here, our My and our Mz right there, that cause the member to bend and also produce normal stresses in our section. So now moving back over to our part B of our diagram here, we can see we have our twisting couple T and our shearing forces Vy and Vz. So these shearing force component and the twisting couple are going to contribute to the shearing stress distribution in our section. So with that, we can come down here to our bottom diagram. We can see our normal and shearing stresses at points H and K. So at points H right up here, we have our normal stress right here, our sigma x, and we have our normal stress right here at K of sigma x right there. And this is plus our shearing stresses over here in part B of our diagram here. We have our tau xz acting at point H, and we have our tau xy here acting at our stress element here at K. So as we wrap up our discussion about stresses under combined loads, we can see that our normal and shearing stresses are used to determine the principal stresses, maximum shearing stresses, and the orientation of our principal planes. So what we want to note about this, though, is that the analysis is only going to be valid to the extent that the conditions of the applicability of our superposition principle and our Saint-Venant's principle are met. So what are these conditions down here? Well, we have these listed out as 1, 2, 3, and 4, and all of these need to be met. So 1 is that the stresses involved must not exceed the proportional limit of the material. Now, the reason for this is that this shows that the method presented here cannot be applied to plastic deformation. So step 2 over here that we need to meet our criteria is that the deformations due to one of the loadings must not affect the determination of the stresses of the others. And last here in part 3, we have that the section used in the analysis must not be too close to the point of application of the given loads. So as we continue on with our topic of stresses under combined loads, we want to take a look at our normal and shearing stresses and realize that these are used to determine the principal stresses, maximum shearing stress, and the orientation of our principal planes. So we can see here over here on the right, we have the elements at points H and H are elements right there showing our combined stresses. Now the normal and shearing stresses shown previously on the other slides are now combined and displayed at points H and K on this diagram off to the right on the surface of the member. We want to take note that the analysis is only valid to the extent that the conditions, the applicability of superposition principle and the Saint-Venant's principle are met. So how do we meet these? What are these criteria? We come down here to 1, 2, and 3. In the first one here, we state that the stresses involved must not exceed the proportional limit of the material. 2, we say that the deformations due to one of the loadings must not affect the determination of the stresses due to others. And last, we can say here in 3 that the section used in our analysis must not be too close to the point of application of the given forces.